At Arizona State University, we're bringing world-class education from our globally acclaimed faculty to you. Earn your degree from the nation's most innovative university. Online. That's a degree better. Learn more at asuonline.asu.edu. At Arizona State University, we've made online education better, smarter, and more personalized so you can go further in your aspiring field.
I decided to pursue medicine once I realized that ASU did have the online program for biological sciences. You're still required to learn the same curriculum. You're still being tested on the same content that anyone would be tested on in person. The comprehensiveness of the program prepared me so well for medical school.
Explore over 350 plus programs at asuonline.asu.edu.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, hidden gravitational waves, dark matter black holes and first stars. Supermagnets may reveal hidden gravitational waves. Scientists have found a new way to possibly detect high-frequency gravitational waves using powerful magnets. These waves are tiny ripples in space caused by massive cosmic events, and finding new ways to observe them could open up a whole new view of the universe. In the past, researchers tried using heavy metal cylinders, known as Weber bars, to catch gravitational waves. These bars would vibrate slightly when a wave passed through them. But the method only worked well when the wave matched the bar's natural vibration. If the wave was a different frequency, it didn't work so well. Now, scientists are taking that old idea and improving it by using strong superconducting magnets instead of metal bars. These magnets are already being built for dark matter experiments, so they are very powerful and extremely precise. The magnets store a huge amount of magnetic energy, much more than the old metal bars could handle. That energy could make them sensitive enough to detect gravitational waves, especially in a range of frequencies that current detectors like LIGO can't pick up well. Here's how it works. When a gravitational wave passes through the magnet, it causes tiny vibrations, almost like a soft shake. These vibrations stretch and squeeze the magnet in tiny ways. Because electric current flows through the wires inside the magnet, those tiny movements change the magnetic field just a little bit. That change creates a magnetic signal that can be picked up by extremely sensitive quantum sensors, called squids. These sensors can detect even the smallest changes in magnetic fields. What's exciting is that this system creates magnetic signals directly, without needing to convert them from mechanical ones, like the old Weber bars did. That makes the setup simpler and less likely to pick up unwanted noise. And because it works over a wide range of frequencies, especially from a few thousand up to 10 million vibrations per second, it could detect waves that other detectors miss. The idea came from magnets already used in dark matter experiments, such as DM radio and ADM-XEFR. These projects use very large, very strong magnets to search for a particle called the axion. Scientists realized that these same magnets could also be used to look for gravitational waves at the same time. While this new method probably won't be as sensitive as LIGO at lower frequencies, it might do better at higher ones, frequencies where LIGO doesn't work well. That would allow scientists to explore a whole new area of gravitational wave signals that we've never been able to study before. To make this work in practice, researchers will need to make sure the magnets are completely shielded from outside vibrations, like cars driving by or footsteps in a lab. This is similar to what LIGO had to do when it was built. The research team is now expanding their work, trying to figure out which kinds of gravitational waves these magnetic systems might be able to detect. They're also looking into even better quantum sensors that could improve the technology even further. If it works, this new approach could give us a brand new way to listen to the universe. Hawking radiation may reveal dark matter black holes. Scientists may be on the brink of uncovering one of the greatest mysteries of the universe, the true nature of dark matter. A new study proposes an innovative method for detecting primordial black holes, extremely ancient and compact objects that may have formed shortly after the Big Bang. The idea is to look for these black holes not through indirect cosmic effects or background radiation, as has traditionally been attempted, but by directly observing their radiation as they pass through our own solar system. This radiation, known as Hawking radiation, is a theoretical phenomenon in which black holes slowly emit particles due to quantum effects near their event horizons. The brilliance of this method lies in the fact that the amount of radiation emitted by a black hole is inversely related to its mass, meaning the smaller the black hole, the stronger the radiation signal it produces. Primordial black holes, which are thought to be much smaller than the stellar black holes formed by collapsed stars, could be radiating detectable levels of energy if they are passing near us in space. Dark matter, the invisible substance that accounts for about 85% of all matter in the universe, has never been directly observed. Scientists only know it exists because of its gravitational influence on galaxies and cosmic structures, yet its exact composition remains unknown. Among the more intriguing possibilities is that dark matter might be made up of these ancient primordial black holes. If that's true, then detecting just one of them directly would be a massive breakthrough. What the researchers propose is that as one of these small black holes zips through the solar system, it should emit Hawking radiation that includes a wide range of particles, neutrinos, photons, and importantly for this study, positrons, which are the antimatter version of electrons. Positrons were chosen because they can be effectively detected by the Alpha Magnetic Spectrometer, AMS, a highly sensitive instrument mounted on the International Space Station. The AMS already collects positron data every day, making it an ideal tool to test this new theory without needing to build new instruments. The team, led by Alexandra P. Klipfel, carried out simulations to estimate how often such a primordial black hole might travel through the inner regions of our solar system and produce detectable radiation. Their findings suggest that this might happen roughly once a year, a surprisingly optimistic result, considering how elusive these objects have been until now. This approach could eliminate the reliance on complex models of galactic behavior or background radiation, which are full of uncertainties. Instead, scientists could get direct and local evidence of these ancient black holes by identifying a sharp, time-dependent spike in positron counts as a PBH moves past Earth. It's like switching from listening for a faint background hum across a city to spotting a car driving past your window. Even more exciting is that this method may not be limited to positrons. The same principle could be used to search for other types of particles in Hawking radiation, like gamma rays or X-rays. These higher energy signals could allow scientists to detect even heavier PBHs, ones that are about the mass of a small asteroid or even a dwarf planet like Ceres. That range of mass is especially interesting, because it represents a key window in which PBHs could potentially make up all of the dark matter in the universe. By targeting that specific mass range, researchers might finally be able to determine whether these elusive black holes are the long-sought missing matter of the cosmos. What's revolutionary about this proposal is that it shifts the entire strategy of dark matter detection. Instead of passively scanning the sky for subtle clues, scientists could actively hunt for individual dark matter candidates moving nearby. If successful, this method wouldn't just confirm the existence of primordial black holes, it would give us detailed insights into how many there are, how big they are, and how they're distributed through space. As our detection tools improve and new space observatories are launched, this strategy could bring us closer than ever to answering the question that has puzzled physicists and astronomers for decades: what is dark matter really made of? And if it turns out that tiny black holes, ancient and cold, drifting silently through space, are the answer, we might finally see the invisible architecture that holds the universe together. First stars may be found in polluted galaxies. Population 3 stars, or POP3 stars, are some of the most mysterious and important objects in astronomy. These stars are believed to be the very first generation ever formed in the universe, made entirely from the basic elements created in the Big Bang, mainly hydrogen and helium. They had no heavier elements, which astronomers call metals, because none had been made yet. Since these stars came before anything else, they are thought to have been very different from any stars we see today, possibly hundreds of times more massive than our Sun. They represent a key piece in the story of how the universe evolved from something simple into the complex and rich cosmos we now observe. Even with advanced tools like the James Webb Space Telescope, JWST, astronomers still haven't found clear evidence of these ancient stars. Most searches have looked for completely pure galaxies, places with no signs of heavy elements at all. Scientists thought that by finding galaxies made only of hydrogen and helium, they could finally spot population 3 stars. But this approach has a problem: it's too narrow. The window to catch these stars before they become polluted by supernova explosions is extremely short, making it very hard to observe them at the right moment. Now, a group of researchers led by Elka Rusta from a university in Italy has proposed a new way of thinking. Instead of looking for galaxies that are perfectly clean and metal-free, they suggest we should focus on galaxies that have just started to become polluted, when the first generation of massive stars has already begun exploding and spreading heavy elements into the surrounding gas, but some of the original population 3 stars are still shining. This phase, called the self-polluted phase, may actually be the best time to find these early stars. It offers a wider window for detection and could explain why they've been so hard to spot until now. During this transitional time, even though the stars themselves are still metal-free, the surrounding gas already carries the chemical fingerprints of the first supernova explosions. This means astronomers can detect specific light signals from the gas, like glowing lines produced by metals, while the stars inside are still the original pristine population 3 stars. This changes the whole strategy. Instead of waiting for a short-lived, perfectly clean galaxy to appear, scientists can look for the telltale signs of this hybrid phase, which lasts longer and is easier to detect. The research team also discovered that a key sign of these early galaxies, strong helium emission, can last up to 20 million years. That may not seem like much, but in astronomy, it's a big improvement over earlier expectations. Even better, this helium signature can still be seen during the phase when both first-generation and second-generation stars are present, giving researchers more time and more chances to observe these rare systems. To help with the search, the scientists developed a set of new tools that look for specific signals in the ultraviolet part of the spectrum. They focus on patterns involving elements like oxygen and hydrogen, using the ratio between certain light emissions to find likely candidates. This method was applied to data from the JWST's Deep Space Survey called JADES, and it worked surprisingly well. They found 9 galaxy candidates that may contain a large population, more than 25%, of metal-free stars, which is far more than previous efforts had managed to identify. This approach is a major shift in how astronomers search for the universe's first stars. Instead of looking for what's missing, which is difficult and uncertain, this method looks for the presence of specific, measurable signs that can be clearly identified. If confirmed, these galaxies could reveal a great deal about how the first heavy elements were created and spread across the early universe. They could also help scientists understand how the universe changed from being made mostly of hydrogen and helium to becoming chemically rich and complex, full of the elements that make up stars, planets, and life itself.
Ready to make a real impact every day? Join the Active Day Home Care team and help clients maintain their independence in the comfort of their own homes. Make a difference in someone's life as you provide essential daily assistance and protect their health and happiness. Earn up to $20 an hour and enjoy additional perks like optional daily pay, 401k, paid time off, ongoing educational training, and more. Join a team that values care, compassion, and your professional growth. Visit activeday.com to apply.
With so many options, why choose Arizona State University?
For me, the only online option was ASU because of the quality. Their faculty was really involved with their students and care about your personal journey. The dedication to my personal development from my professors, that's been extremely valuable to me.
Earn your degree from the nation's most innovative university. Online. That's a degree better. Explore more than 350 plus undergraduate, graduate, and certificate programs at asuonline.asu.edu.